Okay, so let's continue our discussion with turbine engines. We're going to talk about the lubrication system now. Now, the lubrication system does all the same things that a recip engine lubrication system does. There's just a little bit of nuance to it since it's on a turbine. There's things that exist on a turbine that you just won't see on reciprocating engines pretty much anywhere. So we need to kind of talk through the details of that.
Okay, so we're going to start by just breaking down the components. So here is a sample oil tank from the 8083. I won't go into the amount of detail it does about this particular oil tank, but I do want to point out that there's nowhere for the oil to be stored on a turbine engine like there is in a reciprocating engine. So, like you think of in a reciprocating engine, you have a sump where all the oil will run down to, and the crankshaft is constantly splashing itself in it. And that, even though that's the way the system is designed, so that way the crankshaft can reach down there, hit the oil, and then splash oil up into itself. It also doubles as a storage tank, unless of course you have a dry sump system, and that's kind of like we'll just table that for right now. Um, in a turbine engine though, they're all dry sump systems. There's not really another place for the oil to sit, but they absolutely have to have oil because you have to cool the internal components off some way. And you also have to clean it in some in some way. So there's always a oil tank of some variety somewhere. Now the turbine engine that I have the most experience with is the OH58, and our oil tank was behind so you had the turbine engine, and then behind the aft firewall was the engine oil tank, and then the oil cooler and all that good stuff. And it was like this little rubber expandable bladder that basically that's where the oil was kept. Now that one was kind of optimized for combat, so that's why it was that self sealing rubber, so that way you could shoot it and the bullet would just go right through and it would more or less seal itself. Other aircraft are going to have different requirements, different needs, and the oil will be placed in different places to accommodate it. But the so what of this is that like know that the turbine engine has to have a external oil tank of some variety. Okay, so now if the engine is going to consume and use oil, and the engine oil tank is somewhere other than the engine, there has to be some way to move the engine oil from the oil tank to the actual engine itself, and that is done by the oil pump. Now, the oil pump, this is just an example of one. They all have different types that they could be tied into the accessory gearbox and run that way. You could have potentially electric oil pumps. Which I don't know that are the most common. Probably the most common are the gear and generator oil pumps that move oil based on the the engine RPM. As the engine turns, it turns accessory gearbox. The accessory gearbox then turns um, spindle that then turns the oil pump itself that moves the oil from the pump to the engine via a filter of some variety. There's not really just a whole lot to say about these. They're pretty simple, pretty straightforward. They're there to move the oil around. Typically, if you're going to have a oil system failure, this is where it's going to be at, and you can see why. Like if you look at the amount of gearing that happens inside of these oil pumps, you can kind of start to piece together like, oh yeah, like the oil system is probably going to break down right here. It's going to be here or the oil cooler, and we'll get to the oil cooler here in a second. If you look at this one, it's pretty straightforward. The way that it works, it just pulls oil in from the tank. It squeezes it through a series of gears or baffles, and then pushes it up to the oil filter. It'll go through the oil filter and then on to wherever else. There's a relief valve, so if it overpressurizes, it'll pop open and oil will come out that way. The one thing that is kind of interesting and a little bit different on this is notice it on the input shaft. It says the shear section. Most of these are built with an engineered weakness in the drive shaft, and this is true of a lot of different things, not just oil pumps. And the idea is that if something locks up inside of the oil pump, whenever it goes to break, instead of like instead of just stripping out the inside of the accessory gearbox, that shear section will snap, and it will allow for the engine side of the shear section to continue to turn while the oil pump just basically is seized up and sitting right there, and that prevents much more expensive damage being done to the engine in the event of an oil pump failure. And oil pumps are not uncommon to fail. Like I said, there's a lot of moving parts and pieces. They turn at a high RPM for a elongated amount of time. So you think of if you fly across the United States over the course of like 10 hours, 12 hours in like say your PT6 or not your PT6 but your PC12 that's powered by a PT6 or Cessna Caravan or something like that. That's 12 hours of thousands of RPMs, and this is just a little pump. Like eventually, like you're going to end up. I mean, you maintain it and try to keep it going. But if something's going to fail, this is probably one of the chief things that will fail. Okay, speaking of oil pump failures, here's a oil filter, which is our next component we're going to talk about. That's had a oil pump failure, and you can see all of the bits and pieces of that oil pump that's inside of the filter element there. Now, your oil filters, they will generally consist of kind of two elements. You have a filter housing, and then you have the filter element, which is the actual filter itself. The housing effectively sits there like a bowl, and all the oil, the unfiltered oil, goes into the bowl. And then there's a suction in the center of the oil filter that pulls that oil that's coming into the bowl through the filter element and then up into the rest of the system. So therefore, filtering the oil because it's having to come through the filter element that way. Now, this is a piece of equipment that you'll have to change out every 100 hour, all just many times. Like if there's going to be if you see a low oil pressure, or the oil is hot, all those types of things, you could potentially be looking at a new oil filter. So these are very common. They are also very expensive on jet engines. They're going to be very easily a couple $100 every time you have to change it out. There's also a aspect of these that you won't see generally with reciprocating engine. That's the ability to bypass them. So typically, if you see a oil filter, there will be a little red button that can pop up on the time up top. And if that button is popped, that means the filter has been bypassed. Now, the only reason it would bypass is if the oil filter gets clogged for some reason. Let's say there's a bunch of trash in the oil and it filters it out, and all of a sudden it cannot allow enough oil to get through there, and then the pressure on the inside of that bowl gets super duper high because the filter element is just clogged up. It will a valve will open, and as the valve opens, all the oil, unfiltered oil, will go back in the engine, which is a really bad thing. But and you'll typically get an indication in the cockpit that says like, "Hey, look, engine oil filter bypass has been activated." And whenever you look at the engine itself, you'll see like a little red pop it up there. You'll get the same thing with hydraulic fluid bypass. Like you'll see the little red buttons pop up. But it also happens in the oil filter world as well. Now that kind of brings us to our next component. All right, this is a oil pressure regulator or regulating valve that you can see on the top of that little blue component there, on top of the pressure regulating valve. That you could imagine that component being able to be turned from the outside, and that's basically what ends up happening. Typically, these are done with flathead screwdrivers, but you could have a bunch of different things. Now, essentially, during different phases of maintenance, like trim runs, that kind of thing, you're going to want to set the oil pressure. Whenever you know that there's no leaks and the engine's properly serviced, you're going to run the engine up to whatever the maintenance manual tells you to. You're going to see that this is where the engine oil pressure is at, and that it needs to be in a range between, say, like 10 psi and 20 psi or whatever it is. And you'll go back to the engine and you'll turn it up or down to get mid range of that oil pressure. Now you don't want to over pressurize the system because that could cause a lot of problems. Too much pressure in any sort of fluid system will cause damage, damage to seals, damage to hoses, you name it. Under pressure will cause the engine to not get the lubrication it needs. It'll start to run hot. You'll get a lot of friction. You'll have all kinds of problems, and that's a good way to ruin an engine. So you want to make sure that your oil pressure is set correctly. Now, there's also a relief valve that's tied into all of this, where it will effectively the if the system becomes over pressurized, it will open and allow for oil to flow freely, or it'll just be vented overboard, so you get a big oily mess off the side. But typically that's happened because the oil filters become clogged, or some part of the oil system has become clogged. Okay, the next thing that we want to talk about is oil heat exchangers. Now, these can come in the way of fuel oil heat exchangers, air oil coolers. Effectively, all they are is that you're going to take hot engine oil and you're going to put it into a box or have it go through fins or whatever, just like any other radiator. And you're going to take a super cool substance of some variety, and you're going to run it through that box, and it's going to allow for that super cool substance to grab heat off the oil and pull it into itself, and therefore cooling off the oil while simultaneously heating up the substance. Now let's talk about air first. So air's easy because it's very much just like your engine car radiator, right? So as you're driving down the road, that air is hitting that radiator, and it's going over those fins, which has coolant going through it that's super duper hot, just coming out of the engine, and it's going to grab the cool air is going to grab the heat off of that coolant, and it's going to pull it out through the radiator, and then it's going to be dumped overboard. And that's how you keep, then whenever the return line on the radiator is going to be super cool as compared to the super hot air that, or the super hot coolant that was coming into the top of the radiator, right? Same idea, except for now replace the coolant with oil. And think about the air that would be going over that radiator. It could still be air. It could just be like radiator. So like kind of go back to our OH58 example. That's how we worked. Like we had the oil cooler positioned right underneath the rotor, and the rotor would then blow air down on top of the oil cooler and pressurize it and push air through those fins, and the oil would then would be routed through that radiator, and it would help cool the oil down. So typically, if you got a high engine oil, you would check the quantity. If the quantity was good, you'd go through there and we would take a pressure washer and we would blow that oil cooler out, and you get all this trash that would come out of it. Especially whenever we were in Iraq, primarily. Afghanistan wasn't as bad, but Iraq was really bad because we had so much dust and sand. It would just clog that thing up, and you would see the engine oil just start to slowly creep up over time until we washed out the oil cooler, and then it would drop it back down. Now, where it gets really interesting is fuel. Fuel is actually, in its natural state, pretty cool. It wants to be cold, and so whenever you get up to altitude, so you're 20, 30,000 feet, that fuel is going to want to turn around and freeze. If it's got any water in it whatsoever, it's going to want to freeze up. And so you need to turn around and raise the temperature of the fuel. Simultaneously, the engine oil is totally the opposite. It's going to be hot all the time, and it needs to be cooled down. So a fuel oil heat exchanger like you're seeing right here is pretty nifty. You can pipe the fuel through there, and it's super duper cold, and you pipe the engine oil over the top of it, and they have a heat exchange where they kind of neutralize themselves. They kind of come to a nominal level where the oil is cooled down, the heat or the fuel is heated up, and they kind of meet in the middle, and everybody wins. So it's kind of a pretty system whenever you look at that, how well balanced it is. But that's all it really is. Is that we're just trying to regulate the internal engine heat via an oil cooler of some variety. And then there's a bunch of different types that are out there. There's air coolers, there's fuel oil coolers, and you'll see tons of them over the course of your career. Okay, our last component is the oil nozzle. There could be any number of different types that you could get on here, but essentially there has to be something that basically shoots that oil onto a bearing, so that way you can get the oil can get to where it needs to go. Um, that this is a version of that. Notice that the last little bit looks like a cone, and it kind of squeezes that oil down. If we know that we increase pressure, we decrease temperature. So it's the last chance to kind of cool the oil off a little bit before it goes on the bearing. Now, once it hits the bearing, there's going to be some sort of oil return side on there, where you, instead of having a pressurized oil, you're going to have negative pressure on the other side, or no pressure, and it's going to allow the oil to go back into the system to circulate and do it all over again. Now, as the oil goes around those bearings and the rest of the engine, if there's any sort of metal flakes or any sort of trash, it's going to pick that up, which sets us up for our next topic.
Okay, so let's talk about chip detectors. What is a chip detector? Why does it exist, and how do they work?
Okay, so this is a chip detector. Now, what they are, just kind of fundamentally, they are nothing more than magnets that are placed into the oil line. Generally speaking, on the return side. Okay. Now, what's going to end up happening is that as the oil goes by, if there's any sort of metal in the return line, it's going to that magnet is going to grab it, because typically they're these little shavings. So here's an example of a chip detector on the right hand side of this graphic of little shavings that the chip detector has got. Now this engine's in pretty bad shape because that's a lot of shavings. Typically they're just like onesies and twosies. Now where they get really cool is that typically you will have two magnets that are both linked into the engine oil system somehow or another. Now once a piece of a chip, a piece of metal, sits across those two probes, it will complete a circuit, which will then illuminate something in the cockpit. They'll say like chips, engine lower, or chips engine upper, or wherever, whichever chip detector it is. You'll get an indication in the cockpit saying that, hey, look, there is actually a chip on the chip detector, indicating that there's been some sort of engine failure, or at least trash in the engine oil that got through the filter, and now it's inside the engine. And so that's something we need to take care of. We need to drain and service, inspect, whatever the maintenance manual calls for it. Now, some chip detectors go a little bit further than that. What they end up doing is that they'll end up creating a situation where if a chip lands on those two probes and connects it, it will start to run electricity through it to heat it up to see if it can disintegrate that chip and get rid of it right then and there. So sometimes you'll see it'll hit, and then you'll get an indication in the cockpit, hey, look, chip's transmission lower, or whatever the thing is, and then it will slowly, just go away. It'll go because it burnt off the chip. And then there's certain limits that if it stays there for more than so many seconds, you have to do X, Y, or Z. Or if a certain one illuminates, then you precautionary land, and then do all this maintenance right then there, all these inspections. Or maybe if they light up, you just can the engine at that point. Either way, that's how a chip detector works. There will be several of them on an engine. So on the PT6, there's two. There's one right up underneath the prop, and there's one on the very back. On a Allison 250, there is two, if I remember correctly. There's going to be chip detectors all over the whichever aircraft you're working on in places where it makes sense. So typically these are always going to be on the return side of the lubrication system, and it's going to be in a place to catch any sort of failure that could potentially happen. Now, where do these chips come from? You can get them just from the outside environment, but even though it's rare because it has to go through so much filtration that like it would get to a chip detector, but it could happen. All right. Most likely, if you have chips, they're going to be coming from something inside of the engine is starting to deteriorate and fall apart. Typically, it's a bearing, but it could be any number of components. And as those components begin to fail, they start to shed little bits and pieces of themselves. It gets in the engine return line, and it starts to connect those two probes on the chip detector, and that's when you get the illumination light. Now, follow-on maintenance is almost always going to be a drain and service, change the filter, try to see if we can get rid of it, run it up, see if you get chips again, check it every so often, so on and so forth. Sometimes, though, like you're going to turn around and see that, hey, like we have, we keep getting these chips, and we need to know where they're coming from. So this is where your oil analysis comes in. You'll basically fill up a little cup or a little bottle, and you'll put it in the mail and send it off to a lab. They'll come back and say, hey, look, this is 25 parts per million of irons. Therefore, the iron's high. The iron must, like these are the components on that in particular engine that are iron. This is probably what's failing on you. This is what you need to go check. And so you'll go and pull that component off, look at it. Sure enough, there's the bearings going out or whatever the thing is. Certain metals, if they are falling apart, it'll call for a complete engine overhaul or engine swap or whatever. But either way, like that will all basically start with saying like, hey, look, the chip detector illuminated for some reason or another. These are probably one of my favorite components of a turbine engine because it's so simple, but it is super duper cool, especially being able to burn off the errant chip that may happen here or there, wherever. Now, also keep in mind a engine life cycle. The engine will generate chips on the front and back end of its life. The front end is from manufacturing. Is that like, hey, look, this whole engine was just put apart, and no, it doesn't matter how FOD free we keep everything. Whenever we put things together, something is going to generate some trash, and part of your burn-in process is just kind of like bearing with the drama that is produced by these chip detectors picking up all kinds of stuff. And so like during certain hour bands, you're able to say like, hey, look, from 0 to 100, chips are good as long as they burn off within 3 to 5 seconds, or they only constitute so much amount. If during certain other hour bands, like the majority of its life, is like chips aren't allowed, and then towards the end of its life, you're going to start when you start seeing chips. Here's all this maintenance stuff because we're expecting the components to fail because it's been in service long enough to where we kind of know that this bearing is going to go out at some point, and so we're just basically watching for it. And once we get chips, we know that it's starting to happen. Very 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 cool little maintenance component on turbine engines.
Okay, so what happens if our turbine engine starts to excessively just eat oil? What can that tell us?
Okay, so if you get excessive engine oil consumption on a turbine engine, there's a couple of things that you can pretty much look for. Right off the bat is a leak. That's going to be the most common. Something is caused a problem. Some sort of seal has started to break down and it's starting to leak. So if you park an engine and then there's a bunch of oil underneath it the next day, then you can pretty well bet that there's a problem. Point in case, we have an aircraft on the floor right now that something happened to. We're still troubleshooting it, but on the underneath it is a bunch of oil that's just leaking out of the airplane every single day. So it's kind of like a good indicator that there's something seriously wrong if you have an oil leak, and maybe it flies a lot, it doesn't park in the same spot, you haven't been able to notice it, but what you do notice is that the oil log is showing that like it's just eating oil on a regular basis. It means it's losing it somewhere. That oil isn't just evaporating and going somewhere. If it's not leaking, then the place where the oil on a turbine engine is most likely to meet its end is on the seals on the bearing. Now, as those bearings have to have oil in order to stay cool, and so there's seals to keep the oil in there. If those seals start to break down and then they start to leave that bearing, then they're going to get off into the engine. It's going to get effectively burn off through just the excessive engine oil heat. And so you can start to look at the different seals of the different bearings, and you can start to find where your oil leak may be at. And now there's going to be every maintenance manager is going to have some sort of standard where it says that, hey, look, once you have consumed X amount of oil in so many hours, that's cause for concern. But like every engine is going to burn some oil, some way, shape, form, or fashion, just as the oil starts to break down. It's going to turn around and want to get burnt off anyways. Because keep in mind that there's an excessive amount of heat that this oil is being exposed to. Now, and so you want to make some allowances just for reality. But if it starts to becoming excessive, and this is very easily seen if you have a fleet of the same aircraft, you'll start to see one of them just starts eating oil more and more and more. You have an oil leak somewhere, even if it's internal and it's starting to burn off internally, and you're not seeing like puddles on the floor or anything else like that. That still kind of points to the fact that there's something not correct, and you need to start investigating it during your next major maintenance.